Today, we are diving into one of the most important concepts in statistics. Topic 4.1: the sampling distribution for sample means. By the end of this video, you will be able to calculate the mean and standard deviation of these distributions, justify the conditions needed to use a normal model, and interpret your findings in the context of real-world problems. Let's start with the big picture. Imagine you have a giant population, like every student in the United States. You want to know the average height, which we call the population mean, mu. It is usually impossible to measure everyone. So, instead, we take a random sample of, say, 50 students and calculate their average height, which we call x bar. If we take a different sample of 50 students, we will get a slightly different x bar. If we did this over and over again, thousands of times, the distribution of all those different sample means is what we call the sampling distribution of the sample mean. To describe this distribution, we need to know its center and its spread. Let's look at the formulas that define the mean and standard deviation of the sampling distribution of x bar. The first rule is that the mean of all possible sample means, which we denote as mu sub x bar, is exactly equal to the population mean, mu. This means that x bar is an unbiased estimator. On average, the sample mean will hit the target of the true population mean. Next, we look at the spread. The standard deviation of the sampling distribution, denoted as sigma sub x bar, is calculated by taking the population standard deviation, sigma, and dividing it by the square root of the sample size, n. Notice that because the square root of n is in the denominator, as your sample size increases, the standard deviation of the sampling distribution decreases. This makes sense. Larger samples give us more consistent and precise estimates of the population mean. However, there is a catch. For this formula for standard deviation to be accurate when we are sampling without replacement, we must satisfy the 10% condition. This means our sample size, small n, must be no more than 10% of the total population size, capital N. This ensures that the observations are independent enough for our calculations to hold true. Let's put these formulas into practice with our first example. Suppose we are studying the weight of a specific breed of adult dogs. We know from historical data that the population of these dogs has a mean weight, mu, of 65 pounds and a population standard deviation, sigma, of 12 pounds. Suppose we take a random sample of 36 dogs. Our goal is to find the mean and standard deviation of the sampling distribution of the sample mean weight for samples of this size. First, the mean of our sampling distribution, mu sub x bar, is simply equal to the population mean. So, if we took many samples of 36 dogs, the average of all those sample means would be 65 pounds. Next, we calculate the standard deviation, sigma sub x bar. We take our population standard deviation of 12 and divide it by the square root of our sample size, 36. 12 divided by 6 gives us a standard deviation of 2 pounds. Before we can fully trust this standard deviation, we should consider the 10% condition. For this calculation to be valid, there must be at least 360 dogs of this breed in the population. In most cases, for a specific breed of dog, this is a very safe assumption to make. Notice how the variability of a single dog is 12 pounds, but the variability of the average of 36 dogs is only 2 pounds. The averaging process filters out the extreme highs and lows. Now that we know how to calculate the center and spread, we need to talk about the shape of the distribution. This is critical, because if the distribution is normal, we can calculate probabilities using z-scores. Justify the appropriateness of conditions for the sampling distribution. There are two ways the sampling distribution of x bar can be considered normal. First, if the original population itself follows a normal distribution, then the sampling distribution of the sample mean will be normal, regardless of how small or large your sample size is. Second, what if the population is not normal? What if it's skewed or even bimodal? This is where the magic of statistics happens, thanks to the central limit theorem. The central limit theorem, or CLT, states that if the sample size is large enough, the sampling distribution of the sample mean will be approximately normal no matter what the population looks like. For most cases in AP statistics, we consider a sample size of 30 or more to be large enough to satisfy the CLT. If the population is extremely skewed, you might need a sample size much larger than 30 for the approximation to be accurate. So, to summarize our checklist for normality: 1. Is the population normal? If yes, we are good. 2. Is the sample size at least 30? If yes, we are good because of the central limit theorem. If neither is true, we cannot assume the sampling distribution is normal. Let's apply these conditions to a new scenario to see how we justify the use of a normal model. Imagine a pizza restaurant where the delivery times are heavily right-skewed. Most deliveries are quick, but a few take a very long time. The population mean delivery time is 28 minutes with a standard deviation of 8 minutes. Suppose a manager takes a random sample of 40 deliveries and calculates the mean delivery time, x bar. Can we describe the sampling distribution of x bar? First, the manager took a random sample. This satisfies the randomization condition, allowing us to generalize our findings to the population of all deliveries for this restaurant. Is 40 less than 10% of all deliveries? If the restaurant makes more than 400 deliveries in total, which is very likely, the 10% condition is met. This justifies our calculation for the standard deviation. The standard deviation of x bar is 8 divided by the square root of 40, which is approximately 1.265 minutes. Even though the population is right-skewed, the sample size n equals 40 is greater than or equal to 30. Because our sample size is large enough, the central limit theorem tells us that the sampling distribution of the sample mean delivery time will be approximately normal. So, we conclude that x bar follows an approximately normal distribution, with a mean of 28 and a standard deviation of 1.265. By checking these three things, randomization, the 10% condition, and the central limit theorem, we have justified that we can use a normal model to find probabilities for this manager sample. Now that we've established the conditions for normality, let's learn how to interpret these distributions and calculate probabilities. This brings everything together. When we calculate a probability in this context, we aren't asking about the probability of a single individual being a certain value. We are asking, what is the probability that the average of a group is a certain value? To do this, we use a z-score formula tailored for sample means. The numerator is the distance between our observed sample mean and the population mean. The denominator is the standard deviation of the sampling distribution, which we also call the standard error. Let's look at an example involving light bulb lifespan. The lifespan is normally distributed with a mean of 1,500 hours and a standard deviation of 100 hours. If we buy a pack of 4 bulbs, what is the probability that the mean lifespan of these 4 bulbs is less than 1,450 hours? First, let's justify the normal model. 1. The bulbs are a random sample. 2. 4 is definitely less than 10% of all light bulbs manufactured. 3. Even though n is only 4, which is less than 30, the population itself is stated to be normal. Therefore, the sampling distribution is normal. Now for the calculations. The mean of the sampling distribution is 1,500. The standard deviation of the sampling distribution is 100 divided by the square root of 4, which is 50. Now find the z-score for x bar equals 1,450. We get 1,450 minus 1,500 divided by 50. This simplifies to negative 50 over 50, which is negative 1.0. Looking this up on a standard normal table or using a calculator, the area to the left of z equals negative 1 is approximately 0.1587. There is a 15.87% chance that a random sample of 4 bulbs will have an average lifespan of less than 1,450 hours. Note how context is key. We are talking about the average of 4 bulbs, not just one. Let's contrast that last result with a larger sample size to see the impact of the square root of n. Suppose we increase our sample size from 4 light bulbs to 25 light bulbs. How does this change the probability of the mean lifespan being less than 1,450 hours? Remember, our population parameters remain the same. The mean is 1,500 and the population standard deviation is 100. The mean of our sampling distribution is still 1,500, but look at the new standard deviation of the sampling distribution. 100 divided by 5 equals 20. The previous standard deviation was 50, but the new standard deviation is only 20. The spread has shrunk significantly. Now let's calculate the new z-score for that same value of 1,450. Negative 50 divided by 20 gives us a z-score of negative 2.5. A z-score of negative 2.5 is much further into the tail than negative 1. If we look up the probability for z less than negative 2.5, we get approximately 0.0062. Think about what this means. With 4 bulbs, it was somewhat common, about a 16% chance, to get an average lifespan that low. But with 25 bulbs, it's very unlikely, less than a 1% chance. As the sample size increases, the sample mean becomes much more likely to be close to the true population mean. Large samples provide more reliable estimates. This is the law of large numbers in action. The noise of individual variation cancels out as we average more and more observations together. Let's move on to a more complex scenario where we have to interpret everything in context. This is exactly the kind of question you might see on an AP exam. The time customers spend waiting in a checkout line at a local grocery store has a mean of 5.5 minutes and a standard deviation of 4.2 minutes. The distribution of individual wait times is heavily right-skewed because most people wait a short time, but a few wait a very long time. The store manager wants to investigate if the wait times are too long. She takes a random sample of 50 customers and calculates their average wait time. Part A. Describe the sampling distribution of X bar. To describe the distribution, we need the shape, center, and spread. First, the shape. Since the sample size of 50 is greater than 30, the central limit theorem allows us to say the sampling distribution is approximately normal, even though the population is skewed. The center is the population mean, so mu sub X bar is 5.5 minutes. For the spread, we calculate the standard deviation of the sampling distribution. Assuming there are more than 500 customers at this store, the 10% condition is met. Sigma sub X bar equals 4.2 divided by the square root of 50, which is approximately 0.594 minutes. Part B. Interpretation of standard deviation. How do we interpret this value of 0.594? In random samples of size 50, the sample mean wait time will typically vary by about 0.594 minutes from the true population mean of 5.5 minutes. What is the probability that the average wait time for these 50 customers is greater than 7 minutes? First, we find the z-score. Z equals 7 minus 5.5 divided by 0.594. This gives a z-score of approximately 2.53. Using a table or calculator for the area to the right of z equals 2.53, we find a probability of about 0.0057. If the true mean wait time is actually 5.5 minutes, there is only a 0.57% chance that the average wait time for 50 customers would be 7 minutes or more. This would be a very unusual result. Often, students get confused between the standard deviation of the population and the standard deviation of the sampling distribution. Let's clear that up with a visual comparison. Imagine the population of high school students' SAT scores. The individual scores, which we call X, vary widely. If we pick one student at random, it's not very surprising to find someone with a score 200 points away from the mean. That's just one standard deviation. But now, imagine we take a sample of 100 students and look at their average. X bar. The standard deviation of the sampling distribution is only 20. This tells us that while an individual student scoring 1150 is very common, a group of 100 students having an average of 1150 is extremely rare. 1150 is 100 points away from the mean. For an individual, that's only half a standard deviation. But for the average of 100 students, that's 5 standard deviations away. This is a key takeaway. The larger the sample, the tighter the sample means cluster around the true population mean. When you are doing these problems, always ask yourself, am I looking at the variability of one thing or the variability of an average? If it's an average, you must divide the standard deviation by the square root of n. This distinction is the heart of statistical inference. It is what allows us to look at a sample and make a confident bet about what the whole population looks like. Let's explore another scenario to master the justification of conditions, specifically focusing on when a population is not normal. In a certain city, household income is known to be extremely right-skewed, with a mean of $62,000 and a standard deviation of $30,000. A researcher takes a random sample of 100 households. Can we use a normal distribution to find the probability that the sample mean is between $60,000 and $65,000? First, let's check the conditions. The problem states the sample is random, so the randomization condition is met. This allows us to assume the sample is representative. Next, the 10% condition. Is 100 less than 10% of all households in the city? As long as the city has more than 1,000 households, this condition is met. This allows us to use our formula for the standard deviation of X bar. Finally, normality and the central limit theorem. Since the population is extremely right-skewed, we cannot assume the sampling distribution is normal based on the population shape. However, our sample size n is 100. Since 100 is significantly greater than 30, the central limit theorem tells us that the sampling distribution of the sample mean will be approximately normal. Even with extreme skewness in the population, a sample of 100 is generally large enough to smooth out that skew in the distribution of the means. Now for the calculations. The mean of the sampling distribution is the same as the population mean, 62,000. The standard deviation of X bar is 30,000 divided by the square root of 100, which equals 3,000. We are looking for the probability that the sample mean is between $60,000 and $65,000. We calculate the z-scores for both values. Using a standard normal table, the area between these two z-scores is approximately 0.59. So, there is about a 59% chance that the mean income of a random sample of 100 households will fall between $60,000 and $65,000. Let's try one more example that focuses on the concept of sampling without replacement and the 10% condition, which is often a point of confusion. In a small town of exactly 200 adults, the mean height is 68 inches with a standard deviation of 3 inches. The distribution of heights is approximately normal. A researcher takes a random sample of 50 adults from this town. Can we safely calculate the standard deviation of the sampling distribution using our standard formula? Let's check the 10% condition. Is 50 less than or equal to 10% of 200? That is 50 less than or equal to 20? The answer is no. In this case, our sample of 50 is 25% of the entire population. This violates the 10% condition. Why does this matter? When we sample a large portion of a small population without replacement, the individual observations are no longer independent. Finding one tall person significantly changes the probability of the next person being tall because there are so few people left. Our standard formula for sigma sub x bar would actually overestimate the true variability. The result from the standard formula, which would be 3 divided by the square root of 50, or about 0.42, is incorrect here. If the 10% condition is violated, we shouldn't use the simple sigma over square root of n formula. In AP statistics, if you see the condition is violated, your answer should be that the standard formula for the standard deviation of the sampling distribution is not appropriate. However, let's look at the shape. Since the population is approximately normal, the sampling distribution of the sample mean would still be normal, regardless of the sample size. The shape is fine, but the spread calculation is compromised. In summary, the shape is normal, the center is 68, but the spread formula is not applicable because the 10% condition failed. Always check your population size relative to your sample size. If the population isn't at least 10 times larger, proceed with extreme caution. To wrap things up, let's summarize the key rules we've covered today to ensure you're fully prepared for any sampling distribution problem. First, the center. The mean of the sampling distribution, mu sub x bar, is always equal to the population mean, mu. Second, the spread. The standard deviation of the sampling distribution, sigma sub x bar, is the population standard deviation divided by the square root of the sample size. Remember, this formula is only valid if the 10% condition is met, meaning your sample size is no more than 10% of the total population. Third, the shape. We can assume the sampling distribution is approximately normal if either 1. The population itself is normal, or 2. The sample size is large, typically 30 or more, which satisfies the central limit theorem. Take a moment to think about why we care about these rules. In the real world, we rarely know the true population mean, but because we know how x bar behaves, that it centers at the true mean and follows a predictable normal shape, we can use a single sample to estimate the truth about millions of people. Here is a checklist for success. Did I divide sigma by the square root of n? Did I check the 10% condition for spread? Did I check the central limit theorem or population shape for normality? And did I interpret my final probability in the context of the problem? If you can answer yes to these 4 questions, you have mastered the essentials of sampling distributions for sample means. Now you're ready to tackle these problems with confidence. Good luck with your studies.